This is going to be an exciting lesson here. Charging by conduct. Hat hair and clinging clothes from the dryer are two everyday examples of static electricity. The static electricity is the result of two neutral objects made of different materials that have become charged by rubbing them together. How does this happen? Okay, good. Charging by friction is in here. Nice. Okay, so the first one's charging by friction. This is probably the easiest one, probably the one we've come in contact with the most. When neutral objects of different materials are brought together, electrons are transferred from one object to the other. In the process, each object becomes charged. One object is more likely to attract extra electrons and become negatively charged. The other object gives up its electrons and becomes positively charged. Rubbing an object or surface against another creates friction, which speeds up the transfer of electrons. The attraction between objects charged by friction shows that they have opposite charges. The process charging neutral objects by rubbing them together is known as charging by friction. I mean, the figure one's a good example here. So the hair is neutral and the comb is neutral. And when you start to comb them, the electrons are transferred to the comb. So you can see the comb becomes negatively charged and the hair becomes positively charged. And because they have a different, you can see that the hair is now getting a little bit attracted to it. What I've got for you a little bit later in the lesson is a table that shows you which object the electrons would go to. You know, because I mean, in theory, if you didn't know any better, it could go the other way. You know, you comb your hair and electrons go into the hair and the hair becomes negative and the comb becomes positive. That's not what happens. So we'll clarify that a little bit later. For example, when you comb your hair, both the comb and your hair start out neutral. When the comb and the hair are rubbed together, the atoms in the plastic comb have a slightly greater ability to attract electrons than your atoms in your hair. Therefore, some electrons move from your hair to the comb. Your hair is now attracted to the comb. Effects of humidity. You may have noticed that your hair does not stick to your hat on wet, humid days. In humid air, water molecules have more opportunity to bump into nearby objects. During these bumps, water molecules are able to transfer electrons from negatively charged objects to positively charged objects. As a result, charged objects tend to lose their charge quickly in humid air. In dry weather, there are fewer water molecules in the air, so charged objects are less likely to lose charge by bumping into water molecules. Charged objects stay charged in dry weather, making your hair prone to electricity. Basically, this in a nutshell is like your dryer is very dry, and so that's why static electricity starts there. If you could add water into the dryer, then you wouldn't have static electricity, but then you wouldn't have dry clothes, would you? Yeah. Okay, so here is our second way of charging stuff, and this is by conduction. Really, it's just touching objects together. So our first one is friction, where you rub them together. The second one is conduction, where you touch them together. So a neutral object can also become charged by direct contact with another object that is already charged. Charging by conduction occurs when two objects with different amounts of static with electric charge come in contact with electrons and move from one object to the other. Conduction between charged and neutral objects. Assume you have a negatively charged metal rod and an uncharged or neutral metal sphere. Okay, so that's figure one here. So it looks like this rod is negatively charged. It looks like the sphere is neutrally charged. And you can see from the picture here that we actually have electrons jumping from the rod onto the ball. So the negatively charged rods transfer to the sphere by direct contact. The sphere gains a negative charge by conduction. That's essentially what's going on. You touch them together and the electrons can move from one object to another. Maybe I'll skip reading all that. Conduction between two charged objects. Charging by direct contact does not always involve a charged object and a neutral object. There is a difference in charge between two. If there is a difference in charge between two charged objects that are the same, electrons will move from one object with a larger negative charge to the object with a smaller charge. Okay, that's might be a rare case. Okay, good. So that is our first section here. 12.5, I'll give you a second to click on that one and open it up. So this is our third type, and this one's a little weird. It's called charging by induction. I'll give you a moment to grab that. While you guys get that out, I'm actually going to try to open up a link here. I don't think it's going to work, though. We used to have some really good interactive activities that worked nicely. Unfortunately, they ran on Flash. Flash, like, no longer works on anything anymore. I don't know. We'll see if this will work. Anyway, you guys open up 12.5. So you didn't like that. Let me try one other thing before we come back to that. I don't know if you've ever used any of these icons. Sure, maybe I should have done this earlier. I just thought of it, though. Okay, we'll check out 12.5 here in the interim. Charging by induction. This one I like just because it talks about why a balloon will actually stick to a wall. So that's why this section's kind of neat. Have you ever been able to stick a balloon onto a wall after rubbing it on your sweater? How is this possible? You know that the balloon gains a static charge because of the rubbing. You also know that opposite charges attract each other. However, the wall is neutral. How does the balloon stick to it? Induced charge separation. When you rub a balloon against your sweater, the balloon gains a negative charge. If you look at our picture here, it's kind of hard to see, but this yellow balloon actually has more negatives on it, okay? So it's negatively charged. Our wall is neutrally charged. So what happens when we bring this negatively charged object towards the neutral wall? Well, you can see it in the picture here that the negative electrons are repelled. We've learned that. When you have same charges, they're repelled. So the negative electrons are like repelled back into the wall, which leaves the wall surface being positive. And right then and there, you've got your positive wall and your negative balloon attracting each other. And that's why the balloon sticks to the wall. So it's like two things go on. Firstly, you rub the balloon, becomes negative, and then you get into this, and it repels the electrons and sort of attracts the protons. Something was said. Wait, can you actually do that with balloons? You've never rubbed a balloon on your head? Tyler, hey, how's it going? Yeah, that's what I was trying to load up in this demo. It's actually quite a nice little demo. It doesn't want to, I don't know if it's going to work here. I can find it in a bit. But it's actually about, you bring a balloon to the wall and you can see it actually repelling. I'm going to have to look into that a little more. It didn't open up the link, unfortunately. All right, where were we here? All right, so generally this is one of the things I get kids to draw a diagram of in class, as long as we know that it's called charging by induction. So it's like a little bit of charge gets pushed away. That's what's going on there. If I have a latex allergy, if I die, if I rub balloon on me, okay. Maybe don't rub yourself with a balloon then. I guess that makes sense. Have somebody else. Have a parent or adult rub the balloon on their head and then put it on the wall. Anyway, so this whole thing is called induction because you're not really, like, there's no transfer of charge. You're just sort of pushing the electrons away. Okay, so it does go on to explain it here. Let's see. The negative charged balloon is attracted to the positively charged section of the wall. This is why a balloon can stick to the wall. Both the balloon and the wall are poor conductors. Very few electrons move from the balloon to the wall. Wall still has the same number of positive and negative charges, so it's still neutral overall. Just the electrons get pushed away. I guess when you move the balloon away, the electrons will come back. This induced charge is only temporary. The electrons in the wall will move back to their original position once the charged balloon is moved away. Charging more than one object by induction. You can use a positively charged object to induce a charge in a neutral object. And by the way, I do have a nice little demo, not the one, I've got a couple of demos here to show you about this. You can even charge two objects at the same time and make the charge permanent. A balloon with a polyester cloth, the balloon loses electrons and gains a positive charge by contact. If you bring the positively charged balloon close to the neutral metal spheres, it produces an induced charge. Okay, so let's follow this picture here. So in figure A, we have two identical neutral spheres that are contacted. In B here, we've got a positive balloon that comes close. So what you get is you get electrons moving from balloon B, or ball B, over to ball A. And then all you do is you remove the original object, the orange balloon, and then that leaves you with A that is negatively charged and B that has a positive charge. So you're just sort of moving charges around with a charged object. Okay, so all this buildup of charge can be dangerous, so that's why we have something called grounding. You can return any charged object to neutral by adding or removing electrons. The electrons can be transferred between the charged object and a large neutral object, such as Earth or the ground. Large objects, like Earth, can gain or lose electrons and remain neutral because the charges are spread over a huge area. The process of removing charges from objects by contact with a large neutral object is called grounding. You can use the symbol shown in figure 3 to show that the object is grounded. When a negatively charged object is grounded, electrons travel from the object into the ground until the object is neutral. When a positively charged object is grounded, electrons from the ground travel up the positively charged object until it is neutral. So there's a lot of grounding that goes on in our world. Often it's set up so that electrons can travel on your water pipes, of all things, believe it or not. So like a grounding wire could be connected to the water pipe because it's could be copper, whatever it's made out of, but then that'll let electrons flow around to or from whatever you need. So figure 4 shows what happens when a person carrying a negative charge on his hand comes in contact with a neutral faucet that is grounded. So here we go. The electric discharge when the hand gets close enough, so there is an electric discharge when the hand gets close enough to the faucet. The excess electrons are rapidly transferred from the hand to the faucet. He receives a shock and may even see a spark. The faucet is grounded, so the electrons do not stay in the faucet. They travel from the faucet to the ground until both the hand and the faucet are neutral again. So that's exactly what I was talking about. Technicians working on electric devices always make sure they are grounded to avoid the buildup of electrostatic charge that can damage equipment. Objects can be grounded without being attached to Earth's surface. Ships at sea and planes in the air can be grounded. A connection to any neutral object that can store enough excess charge can serve as a ground. In the case of the ship, the ocean acts as the ground. The body of the airplane acts as a ground for the electrical device on the plane. Okay, wrapping this up here. Permanent charge and the law of electric charges. You can apply the law of electric charges to understand how you can permanently charge an object by induction by momentarily grounding it. In figure 5a, as the distance between a negatively charged rod and the side of a neutral pith ball decreases, the force with the electrons in the rod repel the electrons in the pith ball increases. The repulsion induces a temporary positive charge on the side of the ball closest to the rod because the repelled electrons there move to the other side of the ball. The charge of the pith ball furthest away from the rod now temporarily has a negative charge. Sometimes I find it easier just to look at the diagrams and see what's going on than these paragraphs because they try to kind of over-explain it. So figure A negatively charged rod induces a positive charge on the side of the pith ball. Okay, so we got a negative rod here. You bring it close to the pith ball, and the electrons move to the other side. Okay, good. Then what it's saying is the electrons are actually grounded, so if you can ground this ball, you can actually remove the electrons, and you're left with a pith ball that's positive, and you have a negative rod. I don't know why you'd want to do that, but that's that. And an example of induction, too, which you may even be experiencing right now, is your computer screen. And so your computer screen is actually attracting dust, and it's attracting it because there ends up being this negative charge on it, and then the sort of induced force and the dust particles move towards you. Okay, so that wraps that up. Grab some paper. Now, I've got a PowerPoint here, and I've only got some slides that I want you guys to copy. So there are a few we got to copy, but then you can see on this one I put do not copy, and those are the ones we'll just talk about here. So grab some paper. We got our 3 forces of attraction. I mean, we got to talk. No, that's not what I want. Okay, so I'll give you a moment to catch up here. So we covered a couple sections, 12.3 and 12.5, the transfer of static charge, and those are the 3 things we talked about. So I'll give you like 2 minutes to copy that down and we'll move on. And yes, we will be having a quiz following the class here. Okay. So we'll talk a little bit about friction. There's going to be some questions on here and something called an electrostatic series that'll help us decide where electrons are going to move to. It's pretty simple to use. All right, so copy this down. So when two different neutral objects are rubbed together, electrons are transferred between one object. So that's like our key part here, kids, is that we have electrons being transferred. It's sort of our fundamental idea. So it's all about these electrons being transferred. All right, I'll try to leave a minute on each slide here. Let me know if I'm going too fast, so speak up. If you type, I can't actually, I'm in a mode right now where if you type it, I don't actually know anything's happened. I need to hear a voice to stop me. Okay, so the object that gains the electrons becomes negatively charged. I hope to reinforce that idea. Okay. The object that gives or loses the electrons becomes positively charged. Okay. Maybe you don't need to copy this one down. So for example, socks rub on the carpet, clothes in the dryer, rubbing a piece of amber with fur. All right, those are all examples. But so the point is, anytime you rub anything together, by the way, that's a way to figure these out in the future, because I'm going to ask, I'm going to give you a scenario, I'm going to say which of the three it is. If you literally see the word rubbing, it has to be friction. So don't bother copy this. So the amber and the fur are, you can see everything in this picture here, should be neutral. The pen, there it is. When you rub them together, electrons are going from the fur to the amber. So you can see the fur has a negative charge, and our fur has a positive charge, and the amber now has a negative charge. Really, it's just counting up the charges. So if you rub the amber with the fur, electrons transfer from the fur to the amber. Sure does. And as a result, the fur becomes positively charged. Fantastic. Okay, just watch this one here. So we've got an acetate rod and we've got a polyethylene rod. It's all about moving electrons. So, oh my goodness, look at that. That piece of fur has, a piece of something has moved, and it has caused the electrons to transfer onto it. So it's some kind of piece of cloth. It's an unidentified piece of cloth. So the acetate becomes positive. Hopefully you guys can see that. And the cloth is become negative. When you rub the different rod, you can actually have the electrons transfer to the polyethylene rod. So it all depends on your two surfaces that you've got, your two things. So the electrostatic series, this is just a table, and here it is. Now, I don't think you're going to need to copy this down. Usually I'll give a handout of this. In the quiz later on in the class today, I've actually just put this slide right in the quiz. And so this is all about rubbing substances together. So there's a whole bunch of ones. And this is actually pretty simple to use here. Oh man, I went past it. So when two different materials are rubbed together, the substance higher on the list always loses electrons and becomes positive. So that's all we just got to look for, the one on the list that's higher up. And the one that's on the lower on the list is going to become, so the one on the lower list gains electrons. I guess the one higher up becomes positive. I think I said that backwards there. So why don't we just take a look here? Here's, I don't know, hopefully this is big enough. And again, we don't need to copy this, but I'll write the answers in. So when glass and cotton are rubbed together, so first thing you gotta do is just gotta find, okay, where's glass? There's glass. Secondly, there's cotton. It also says on the side here that the higher becomes positive, the lower becomes negative. So let's see. The glass is higher up in this situation, so it should become positive. And the cotton is lower in this situation, so it should become negative. That's our first example. And then we've got a second one where we've got hair and rubber. So let's see, where's hair? Hair is pretty high up, and rubber is right near the bottom. So it looks like rubber should become negative, and the hair becomes positive. Let's double check my answers. Yeah, got it. So again, just look at this little part here. This sort of tells you. Again, the higher one becomes positive, the lower one becomes negative. It should be that easy. Just remember that when you do the quiz. Okay, so let's get this down. So here's our definition of charging by contact. And the word touch is the important word here. Friction, the important word is rub. Touch is the important one for charging by contact. Okay, moving on here. Charging by contact occurs when electrons transfer from the charged object to the neutral object that touches it. You know, let's not bother copying that. It's a little wordy. Charging by contact, the neutral object now has the same charge as the object that touched it because electrons move from one object to another. Again, no reason to copy that down. And here's an example. Oh, I don't think I took this out of our textbook. So you can charge by contact using a metal leaf scope, which is a very thin metal piece. So this right here is just a piece of metal. And what it's saying is we're bringing this negatively charged rod close to it. So those electrons that are in the ball originally are getting pushed down. And you can see that there's a positive charge that remains. So if you wanted to make it positive, I guess you'd have to bring a different rod along. Another one just to look at, if you want to determine if an object is charged, you can use a metal leaf electroscope, which is actually designed to detect static charge. Okay, great. See that things are spreading out here. Not really interested. Okay, that's it. So charging by contact, I think all we need to do is have the definition. It's all about touching things together. So friction was rubbing them together. Contact was touching them together. And induction is bringing them together. So without direct contact, that's like the key phrase here. So take a sec to jot that down. Okay, everybody good here? Okay, so here's another example. This is just the balloon example that we talked about. So I don't think we need to read that one over again. And here's a picture of the balloon. So we've got a negatively charged balloon. Again, count the charges. You can see that in our wall here, we've got all positives lining up on the front because the negatives have been repelled back. And so you have a positive negatives. So this is going to stick together because positives attract negatives. Another example, this is about the metal leaf scope one. Again, one of these, you're bringing a negatively charged rod closer, and what's happening is the electrons are actually moving up, moving towards the top here, and this thing actually spreads out. It actually opens up, and you can actually see that in my next slide that is a demo here, so check this one out too. The gold leaf electroscope. That's a pretty sweet electroscope somebody made, and it's all neutral at this point. And we're going to bring a positive rod near it. So we've got to think, what are the electrons up here going to do to this positive rod? What are the electrons down here going to do? Let's see what happens. All those negatives are getting attracted up the rod. There they go. And look at that. This here spread apart. And it's spread apart because everything's positive. And we learned that like charges repel. Now, you can also have the other scenario where you bring along a negatively charged rod. And now it's actually going to repel the electrons away, but the same result. You still get this foil here spreading out. And it spreads out because it's all negative now. And again, negatives repel. So no matter what, as long as you're bringing a charged rod near this device, this thing is going to spread open. That's that. I think I just want to add one other thing that you guys have sort of copied, but let me just add that here. Just a quick summary, if you will. I'll do that. So, again, just to help you out here, when you have friction happening, you've got rubbing happening. When you're talking about conduction, you're talking about contact, so touching. Somebody typed something a while ago. Remember, I can't see it while I'm in that mode. And the one we just talked about was induction. And it's like bringing them close together. So there's no touching. Bringing things close together. No touch. The reason I did this is, again, there are some questions on your homework that you're about to do that I give a situation. You know, you rub your feet across the floor. Is it friction, conduction, or induction? And you need to say, okay, feet are rubbing. It's got to be friction as the answer. I'll come back to this slide. I'm just interested something was said. Sweet. So another short lesson. Again, some of you guys never did the quiz from yesterday. Quiz from yesterday was probably the fewest attempts I've seen. In fact, both physics quizzes, they haven't been well done. I'm giving you time to do it.